will also talk about verification or formal methods for differential privacy.
Thanks, Marco. It's a great pleasure to be here to talk about our research on proving differential privacy via relational types. My background is also in programming languages, so this is about formal methods. This is based on joint work with my colleague Dan Kiefer at Penn State and our students Yu Guanhong and Yu Xin. This project is supported by NSF. So in this workshop, I believe I don't need to convince you that differential privacy is a very useful and rigorous tool for protecting data privacy. Because of the popularity of differential privacy, so we have seen a lot of tools created just to make it easier to develop software which guarantees differential privacy. Thank Dave for the great introduction for Pink, so that's one of these kind of tools. Although these tools are a little bit different in their implementation and the designs, you can think they work roughly in the same way. So first, they either analyze the sensitivity of the queries, like in the fuzz or defuzz system, or require the programmer to annotate what is the sensitivity of those inputs. Then these tools use, instead of verify the basic differential privacy mechanisms, such as the Laplace mechanism for differential privacy. Right? So if I know the data is one sensitive, then I can apply some Laplace noise to it to make sure the result is differentially private. Then all of these tools rely on a very important theorem in many definitions of differential privacy called the composition theorem. So that just means if each query carries a cost of Q, then total cost for the entire software with K queries will be K times the cost of each query. Right? So this is pretty fundamental in all of these tools, making these tools pretty useful, but also limits its usefulness. So to make that clear, let me consider one question that we want to answer. So the question is, among a lot of one-sensitive numerical queries, I want to learn how many of them are above a threshold, say T. Okay. So if you use these kind of tools to develop an algorithm, I bet the best algorithm you can develop and by those tools is this one, the naive algorithm, which applies the Laplace mechanism to each query. And each query you will pay the cost of epsilon, and at the end you get a privacy cost of K epsilon due to the composition theory. So these tools are pretty useful if you only want to implement these naive algorithms. But in fact, a lot of times in reality, we want more sophisticated algorithms, which actually requires more advanced proofs instead of the proofs you can derive from the composition theory. So one example I have is the sparse vector technique. So it answers exactly the same question, how many queries are above a threshold T, but this clever method actually answers the same question in a more accurate way. I will show you the code of SVT shortly, but intuitively the algorithm only pay cost for the queries that are above the threshold, making it more precise than the previous algorithm where each query carries some privacy cost. Okay. The fact is that you can't use the previous tools to show that this algorithm is actually epsilon private. So if you use the previous tools, you can only show it's K epsilon private instead of epsilon private. So there's a missing gap. And moreover, what it makes more subtle is that we have the correct version of SVT, and we have actually a lot of variants which tweak the original algorithm a little bit. There are papers published about those variants of the SVT with some paper-based proofs. And in fact, researchers found that some of the proofs and some of the algorithms are actually incorrect, even though they are peer-reviewed. Okay. So the takeaway message here is that for those very important building blocks of differential privacy, or you think those differentially private core algorithms, core mechanisms in the differential privacy system, a lot of them are very subtle to prove. And like the SVT algorithm, even if you change a small part of the algorithm, you believe your tweak is still correct, but actually the paper-based proof is not trustful. So a lot of times people just make mistakes in those paper-based proofs. So we want formal methods. Okay, so in programming languages community, we have studied formal methods for decades. And this talk is about how we can apply some formal methods to mechanically check that some of the algorithms are actually correct, provably correct. So in particular, in this talk, I will talk about two programming models, namely the LightDP and the ShadowDP. So there are two programming languages for designing and verifying the correctness of differentially private algorithms. When we design these programming models, there are kind of four goals in the design. The first and the most important goal, as in most formal methods, we want to guarantee soundness, meaning that a verified program provably satisfies differential privacy. So if I verify the program, there's no way that the program can go wrong. The second goal here is to make it expressive. So we want the verification mechanism to verify as many sophisticated algorithms as possible, including the SVT technique. We also want this verification mechanism to be useful. It's a little bit challenging because at the end of the day, this tool should be used by someone who designed differentially private algorithms who are not necessarily an expert in formal methods. So we want to reduce the overhead, reduce the annotation burden and the learning curve for the tool as much as possible. And finally, we want to make the tool extensible by using those off-the-shelf program verification tools instead of reinventing those tools from scratch. Okay. So here is a very high-level overview of our programming model, how we can make that happen. So when you design and verify algorithms so this is a LightDP example. In LightDP, this is how the verification looks like. So LightDP have this program. It's a programming language which is very similar to the C or Python language. So you write so here is the example of SVT. So you write your algorithm in this language. So what happens here is first we draw some Laplace noise with some scale factor and add that to the threshold. So we get a noisy threshold tilde t. For each query, we also add a Laplace noise to the query. And if the noisy query is above the noisy threshold, we output a true. Otherwise, we output a false. And this algorithm also limits how many of truths you output eventually, because each true output will consume some privacy budget. So although this algorithm looks very short, as I argued before, it's actually very subtle to prove its correctness. And even if you just change a very small part of the source code, you might get something that is not differentially private. So in order to verify this source code in LightDP, so that's the algorithm you write down, and the programmer also provide a few annotations, which I will talk about shortly. So with those, the verification can go automatically. So basically, all the thing that the programmer need to offer is these annotations, as well as what's the implementation of the algorithm. So with that, we will develop a type system. Will take source code, annotations, and check your source code automatically. If the check pass, the type system will generate something we call the target program, which is very close to your original program, but it also have a distinguished variable v epsilon. So the importance here is this variable here bounds the maximum budget cost. So the maximum amount of differential privacy cost is bounded by the value of this v epsilon by some mechanism in the type system, which I will explain. Because of this, the target program can actually be analyzed by some off-the-shelf verifiers. So that's something we have studied in programming languages community for decades, how to verify that a variable is always bounded by some constant epsilon. So we can use some existing tools to verify that. And the type system guarantees that if both of the check pass, that means your source code is epsilon private. So that's a very high level view of what's going on here. And let me go into some details of what's the magic in this type system here. So throughout the talk, I will assume the pure differential privacy or the epsilon privacy. How to extend our mechanism to other definitions of differential privacy, that's still a future work. So in pure differential privacy, we have some database and adjacent database. So your program is basically an algorithm which runs on the database and generates some distribution because of the noise injected to the data. So epsilon differential privacy just specifies that for the final distributions running on two different databases that are adjacent, the ratio of the probability of seeing the same value in two distributions is bounded by e to the power of epsilon, where epsilon is a constant. Right? So that's the pretty standard definition of epsilon privacy. Now let's see how we can prove this kind of property in a programming language. So there are a lot of techniques to prove differential privacy, and not all of them can be embedded into a programming language. So the technique we use is called randomness alignment. So the key idea here is, in order to prove differential privacy, I try to construct some injective relation between the points on two distributions. Okay, so eventually I want to show that these two distributions are very close. So I do that by create a function, an injective function. So if you give me any point on the left, the function will give you a unique point on the right. So that we require it to be injective. So to see how that works, so let's consider a Laplace mechanism. I just draw a Laplace noise and release the Laplace noise. So there's no secret, no private data, so it should be zero private, right? So the way to prove it is we create this function here. So I map arbitrary v on the left to the same value on the right. So I add a 0 just to make it more generalized. So we call the 0 part the distance. So this is just a special case where the distance is 0, and this is identity function, which is obviously injective. So based on this definition, I can show that for any value v, the probability of seeing v in the first distribution is the same as the probability of seeing the same value v on the second distribution. In other words, this is zero differentially private, right? So what to make it more interesting is if we add some private data, let's say q, and q, by definition, it differs by exactly 1 on d1 and d2. So q can be different. So how can you release some p which depends on q? So the idea is that we can change the map a little bit. So instead of the identity function, we can map a v to a v plus 1 to the second distribution. When you add error to q, both differ by 1 in the opposite direction, the difference will cancel out. Okay, so if you do the alignment in this way, so basically what we can show is the probability of seeing v, the ratio or the privacy cost is bounded by 1 over r because of the property of Laplace noise. And because of that, we have difference of 1 for error and difference of q by 1 in the other direction. So we can actually show that the value of p will be identical. So if you think about what's the injective function on the value of p, so that will be an identity function. Because it's an identity function and because of the relation here, we can prove that if I release the value of p, it's 1 over r differentially private. Okay. So this give you some idea of how the key proof system in the language works. And one nice thing about this proof system is that the proof is basically here. So that's how you align the noise. Okay, so the key of the proof is how to create this injective function. And we can embed that into a programming language in a pretty nice way. So we can embed that into a type. So in LightDP, a type looks like this. So you have the B, which is a base type, like the integers, booleans, doubles, and so on. So what's new in our language is this D. So the D is a numerical expression which specifies the distance part of the previous injective function, or we call it the alignment for the random noise. Okay. So for example, if I write a type in this way, num just means numeric type. If I specify a distance of 0, that just means it has an injective function, which is identity. So I map any value u to the same value u. If I put 1 for the distance, then I will map any value v to v plus 1. So what's powerful in this LightDP language is this D can be some arbitrary program expression. In type theory, we call that a dependent type. So that really makes it very expressive, very powerful to verify the SVT. So for example, I had these two types. So one have a distance 0, and the type of y depends on the value of x. Okay. Then if you think about the joint distribution of x and y, so if I have a state where x is u and y is v, the related memory, the related state will be x have the identical value here, and y will have v plus u, according to your annotation there, according to your injective function. Okay. So in more principle, if you think about a program may have a lot of variables. So in the end, this gamma, the type environment or the types of the variables create some relation between two memories. Each memory have multiple variables, and two memories are related if any variable is related by this gamma. And moreover, we can lift this definition to distributions of memories, so that we can also relate two distributions instead of two concrete memories. So that's the key insight behind this D, the key part of LightDP. So that's the annotation that the programmer needs to write down. Then the LightDP system will verify the program in a pretty automatic way. So let me try to formalize what we can guarantee by the type system. So this is a standard way of formalizing a probabilistic program. So you have arbitrary initial memory. You run a probabilistic program on the initial memory. What you get is a distribution of possible final memories. In differential privacy, we care about two executions of the probabilistic program. I have the original database here. I have the adjacent database here. In the programming language world, I call them memory instead of database. Okay. I run the same algorithm on a different set of data, and I get another distribution. So intuitively, the goal is to prove that these two distributions are very close, or it satisfies the differential privacy definition. If I use the gamma, the injective function I just introduced, that actually can be specified in this way. So if I start from two memories which are related by this injective function, so initially they are just this adjacent database definition. In other words, if I start from two adjacent databases, if I execute any well-typed program, it's guaranteed that the final distributions are still related by this gamma, the types or the alignments in the types, with some privacy cost, which is bounded by this special variable v epsilon. So this is at the high level what the type system guarantees. Yeah. So for any well-typed program, this relation holds. If the relation holds initially, then the relation holds on the final distributions. So now let me tell you a little bit more on what it means to be well-typed in the LightDP language. So this is how the type system in LightDP looks like. At the high level, the type system takes your source code, the annotations. It checks the source code. So this notation here means I check the original command C under the typing environment gamma. So I check it. There are a couple of restrictions which I will show you next. If the check pass, the type system will generate a program C prime we call the target program. So that's how, at the high level, how the type system look like. And these are the restrictions to check in the type system. If this is the first time you see a type system, I guarantee this is the only programming language intensive slide throughout the talk. Okay. So you don't need to understand these annotations too much. So what it says is above the bar, those are the restrictions, or those are the checks the type system need to do. So the first check here is if this is assignment, I need to get the type of E, which contains the base type and the difference, the alignments. I also can get the definition of X, which have this B and D. So this is where the check happens. So I make sure that the tau agrees with the type of X, which makes sense because you want to assign the value of E to X. So it must be true that the base type match as well as the alignment also match. So that make it, so this is where the check happens. What's more interesting is the second rule here. In the second rule, I have a Laplace noise on the left in the source code. According to the type annotation, I want to make it differ by the amount of D. So some expression, I want two noise into distributions to differ by the amount of D. So this is where you pay a privacy cost, right? Because you have some difference in the probabilities. And by the Laplace noise, I know that the difference is exactly bounded by this D, absolute value of D over R. So this is where we make the privacy cost explicit in the transformed code. Okay, so previously you need to reason about the difference of two distributions. The type system makes the difference very explicit here. So it's just the value of this special variable V epsilon by a couple of guarantees of the type system. And also we transform away the probabilistic program into a non-deterministic program. So let me show you what is the difference between the source language and the target language. So this is the source language where you have assignment, branch, loop, and there's a special command which is called a sampling command. So eta is a sample and a G is some random distribution. In the target code, the sampling code is replaced by this havoc instruction. So semantically, the havoc just set this X to be arbitrary value. The very important thing here is the source language is probabilistic, so it's a distribution, but the target language, because of the replacement, we replace it to a non-deterministic program. So there's no probability anymore, there's just, it's only about possible values that this X can take, which actually brings to a very favorable result. So on the target language, there's nothing special from the program verification perspective. So we have studied this problem for decades. So this is called a safety property. So the task for the target program is I want to verify the special variable V epsilon is bounded by some constant epsilon, the desired property, the desired privacy bound in any possible execution. And because this is not a probabilistic program, it's known as a safety property, and we can just reuse those off-the-shelf tools we developed from the program verification community, like HoroLogic, model checking tools, to finish the final step, to check that the V epsilon in the target language is actually bounded by some constant. So I have described all the pieces of LightDP. Now let's put all the pieces together and give you a more faithful view of what happens in the verification. So first, the programmer writes down the source code in the LightDP language. It's just like C code or Python code. So there's nothing special here. The programmer will need to write down these types. The type contains the difference or the alignments I described in the proof. So each type have the numerical part, the base type part, and the distance part. So this is the only annotation we require from the programmers. And a 0 here just means it's not private. So in two adjacent databases, the value of this variable doesn't change. And this thing here describes the alignment strategy, but I will not go into that. But this is the most complex kind of expressions distance you can find in our proof. So these annotations, they can either come from a programmer, or we also have a type inference algorithm which can automatically infer most of these types just to reduce the overhead furthermore. Okay. So this is only annotation required from the programmer. From this step on, everything is automatic. So the type system takes the annotation, the source code. It type checks the source code according to the restrictions described by the typing rule. And in this case, it succeeds, so we will generate a target program. In the target program, each Laplace mechanism is replaced by a have instruction saying that this random sample can be arbitrary value. And we also adjust the privacy cost according to the alignment. So this is the target program, and the goal in the target program is to prove that the V epsilon, the special variable in the target program, is bounded by some constant epsilon. The main theorem of the type system states that if the program type checks and this target program, in this target program, V epsilon is bounded by epsilon, then your source program is epsilon private. And as I said before, this is just some pretty standard program that we can use an off-the-shelf verifier to check its correctness. So in our experiment, we use the CPA checker, a model checker, to verify this code. And this code can be verified without any annotation from the programmer. So it's completely automatic. Okay. So let me quickly wrap up what we developed in this LightDP language. By looking at revisiting those goals I set up initially. So first, we proved a soundness theorem saying that any verified program probably satisfies differential privacy. For the expressiveness, we verified the sparse vector technique and other algorithms by LightDP. For usefulness, the programmer only needs to specify the distances in those types, so the small d's in those types, and furthermore, most of them can be automatically inferred by the type system. So there's really not too much work to do by the programmer. For extensibility, we can reuse those off-the-shelf program verification tools. The target program, it can be readily analyzed by those verification tools. So that's the LightDP system, which makes a pretty good progress towards formal verification of differential privacy algorithms. And so that's the work in 2017. And we realized that there's one limitation, however, about our design so far. So the limitation is that we are not able to verify the report noisy max algorithm with a tight bound. So you might ask why this is important. So there are two reasons. One is this report noisy max, it's a pretty useful building block of like the exponential mechanism in differential privacy. And the second reason is that there's another proof technique based on programming languages, on the coupling-based proof, which we will hear in the next talk, I believe. And that technique can verify this report noisy max. Okay. So the question naturally is, can we use the same kind of argument to prove this report noisy max? So that's something we have done recently. And the answer is, of course, yes. So let me first show you why we can't just readily verify the report noisy max. Then I will show you the key idea for the new technique we developed. So this is the report noisy max algorithm. So the input is a list of query answers with sensitivity of 1. The goal is to output the index of the largest query answer. Of course, we want this to be differentially private, so the accuracy is subject to some privacy constraints. So the source code looks like this. So I look at each query in the query list and add a Laplace noise to each of them. If it's better than the answer, the best query I have seen so far, then I update the index of the maximum query, and I also update the best value I have seen so far. Okay, so it's, again, a pretty straightforward code. But in terms of verification, there's actually some challenges for this piece of code. So let's reuse the alignment idea. That's a key idea behind this kind of proof. So a proof, it boils down to generate a alignment for the noise in the system. So this is actually the best alignment we can get in the LightDP system. So the alignment strategy is align the adder, the random noise, by exactly 2, when a new max is found on the original database D1. So we look at the execution on D1 and try to construct this alignment on the way. Okay. So this is the best strategy we can come up with in the LightDP system. So because of this strategy, so when you see the Q1, which is the second query on D1, and in this case we have a random noise 2. So the new noisy answer will be 4, which is greater than the previous value you have seen. So in this case, the max will be updated. The index of the maximum query will be updated to 1. And in this case, we will align this adder, the noise in the second execution, by 2, by exactly 2. Okay. And by doing that, you also pay a privacy cost of epsilon. So you might wonder, why do I want to pay a privacy cost of epsilon in that case? The reason is that if you do that, it's guaranteed that the best query on D2 is always greater or equal than 1 plus the best query on D1 because of the sensitivity assumption. So the sensitivity is 1, and I add the noise on the D2 by 2. So it's guaranteed that the BQ on D2 is always greater or equal than 1 plus the BQ on D1. So the consequence is that if D1 doesn't update the max, if I reuse the same bit of noise, it's guaranteed that D2 will not update the max as well. In other words, because of the way I do alignment, if D1 doesn't update the max, there's no privacy cost. So I will just reuse the same random bit from the first execution, or in other words, the alignment is 0, and I don't pay any cost because I do this alignment in this way. So what makes it not precise is if I come up with a new query answer where D1 really wants to update the query index. So in this case, the noisy answer will be 5, which is larger than the previous query answer. So I will update the index to be 3. And in this case, I also need to align the adder by 2. So this bit will be 1 plus 2, 3. Just to guarantee that D2 will also update the index to be 3. Okay. By doing that, now the privacy cost is 2 epsilon instead of epsilon. So even for this simple example, by the LightDP-based proof, we can't show that it's epsilon private. We can only show it's 2 epsilon private instead of epsilon private. Okay. So the problem is not the alignment technique is wrong. It's just it doesn't fit into this scenario. It needs some change. So to show you what's the best alignment we can come up with, so this is the best alignment strategy we can come up with. So the strategy is to just align adder once and only do that for the maximum query among all of the queries. Okay, so basically the intuition is that you look ahead, you look at all of the noisy answers on D1, and for the one that is the maximum, you change the noisy answer, the noise to be 1 plus 2. For all the rest of the random bits, you just reuse the same random value from the first execution. It's guaranteed that this strategy will work out. So it's guaranteed that the final result of max will be identical in the 2 runs. But there's something strange here. Something strange is that you need to look ahead you need to look at the future queries as well as the future noise you get from the Laplace in order to construct this proof, which is not very good. So the technique we propose is something called shadow execution. It's a very simple idea. So the idea here is we track two executions on the adjacent database. One is called the aligned execution, one is called this shadow execution. So the shadow execution differs from the aligned execution in the way that in the shadow execution, we always use the same random bit as the random bit you get from the first execution. In other words, the alignment is always 0 for the shadow execution. The benefit is that because the alignment is always 0, we never pay any cost if we use any value computed from the shadow execution. Okay. So that actually allows us to construct a proof. So for the aligned execution, it's the same as strategy 1. I align error by 2 whenever I see a new max. So initially, I see a new max, so this alignment will be 2. So 0 is aligned with 2 in the aligned execution. What's interesting is during the execution, I can actually switch between the aligned version and the shadow version. So one way to think about it is I actually track another option for the proof. That's the shadow execution. Sometimes I can switch my proof to the backup proof. Okay, so in this case, if I see a new max in the for the execution on D1, I will switch to the previous execution on the shadow. So the shadow values will be used, and the new random bit here will be aligned by 2. Okay. The next query, it doesn't update the max, so I still use the previous proof. So I don't update the previous proof. And because the max is not updated, by the alignment strategy, this random bit will still be 1. And finally, I will see a new max in D1. So in this case, I will switch to the shadow execution. And for the current query, I will use the alignment of 2 because of the alignment strategy on the first execution on D2. Okay. So finally, what we construct, it's exactly the same as what if you look ahead. So it's exactly the same alignment as I showed you before in the alignment strategy 2. But this doesn't require any look ahead semantics or in the programming semantics or in the programming logics. Okay, so the change in this new system called ShadowDP is basically we track two versions, two extra executions on the adjacent database, and both of them are described by a D. Okay, so intuitively, the ShadowDP extends LightDP by tracking 3 executions at the same time. You might think, well, that might make it much more complicated for the programmer to verify the code. But we also did a lot of work to simplify the design. So at the end of the day, the programmer actually still only need to write down very simple annotation in the source code, even though the type system underneath tracks 3 executions at the same time. So this is only annotation required from the programmer. For each sampling command, we require the programmer to write down which execution do you want to pick. So you want the shadow execution or you want the aligned execution, and what will be the alignment for the fresh noise you get. So that's the only annotation. And due to the sake of time, I wouldn't explain this very carefully, but this is exactly the alignment strategy I showed you previously in the example. Okay. So you can specify when to switch between the shadow execution and the normal execution, and how much you want to align the new fresh variable, the fresh randomness you get from the sampling command. So to wrap up this new work, so in terms of soundness, we still have the soundness theorem saying that a verified program is satisfies differential privacy. Compared with LightDP, this is strictly more expressive than LightDP, because LightDP can be thought of as a version where the shadow copy is never used. The usefulness, we don't sacrifice usefulness due to the improved expressiveness. The only annotation required is on those sampling instructions. And finally, we can still, the rest of the procedure is the same as LightDP, so we can still reuse those off-the-shelf program verification tools. So this is some evaluation results we have on a couple of differentially private algorithms, and how much time we spend on type checking and how much time we spend on verifying the target program. We have a prototype which is open sourced, and we are still making it more useful for average programmer. But the message here is that it's very quick to type check the source code, and it's also very quick to verify those target programs to finish the last step in the formal verification. In summary, what both the LightDP and the ShadowDP system guarantee, so the core is a relational dependent type system. So the type system actually decomposes the differential privacy, some property on distributions, into some subtasks on non-deterministic programs, which make it much simpler to verify it in a formal way. Due to the lack of time, I will not describe another work happening at Penn State. So the idea is that it's great if you can verify this code, but what if the code is wrong, it's buggy in the first place? So it would be ideal to find some common examples from the believed differentially private algorithm and show that it's actually not differentially private. So we proposed a statistical method of finding common examples when the algorithm violates differential privacy. And if you are interested, both Dan and I will be very glad to talk about more details and answer your questions. And this is a paper which contains more details about this statistical method. So that's the end of my talk, and I'd be happy to answer questions.
Unfortunately, we don't have too much time for questions, but we have a question from somebody that is attending remotely, and he's asking, can you comment on the relation between the distance, I think, on your randomness alignment and the bus time distance?
Yeah, sure. So this system is a little bit like fuzz, if you know what fuzz is. The difference is in fuzz, you track the sensitivity, meaning that the upper bound on the difference. Okay, so a fuzz distance 1 means that the difference between two related executions, the difference is upper bounded by 1. In our system, we are doing this alignment proof. So what we need is the exact difference between two values to finish this proof, the injectivity. That's the answer for that question.
We can take one short question.
Awesome. Let's remember I've forgotten my question by now.
I can take it offline.
Is verifying in? So the better question is, why does it stop at one shadow execution? Like one could imagine.
Yeah.
Like if you're running many sparse vectors sort of in parallel with the same loop, then what, does it explode, or 3 is always enough?
That's a good question. So the question is, why one shadow execution? Why not multiple options for the proof, right? I think there's a fundamental trade-off between the expressive power and the usefulness. So what we find is this is a nice sweet spot. So we can prove use for algorithms without making the type system crazy complicated.
But it seems to me that this is like a good way for you to backtrack.
Yes, exactly. Yes.
And usually you don't need a real, I would think in terms of backtracking, so that you need just to, you committed, but then you want to change your mind, so you go back and you restart in some sense. So you don't need really exploring many paths in parallel, or at least
yes.
Doesn't seem, I cannot see an example where you would explore multiple in parallel.
Yeah. Thanks.
Okay, let's start.